In this video, I'll be doing a very quick introduction to electromagnetic radiation. And the purpose of this is to help us understand how to read the emission spectra from the Bohr model when we discuss about it. So now, let's define what electromagnetic radiation is. Electromagnetic radiation is basically a type of energy that travels through space at the speed of 3.0 times 10 to the 8 meter per second, or also known as the speed of light. And so example of electromagnetic radiation includes the light that be emitted in the emission spectra that we see in a little bit, or the lights that are produced by the sun, or the heat wave that we feeling from a hot object, or the microwave that being produced inside the microwave to heat up our food. Those are examples of electromagnetic radiation. And they can also be referred to as a photon. A photon is basically a package of energy, and it is an electromagnetic radiation. And in this case right here, a photon is basically a particle. And in fact, it is a massless particle, and it has wave property to it. So it is an electromagnetic radiation. Now, how much energy does this photon or this electromagnetic radiation have? It depends on its wave property. So it has wave property that can be used to explain how much energy that it has. So now let's go over some of the characteristics of the waves. So here is a wave right here. And some of the terminology that perhaps you should be familiar with include the crest, the trough, the wavelength, and the frequency of the waves. So in this case right here, the distance from one crest to another crest is then referred to as a wavelength. And that is the same distance from one trough to another trough as well. So when either measure from crest to crest or from trough to trough. And that gives us that wavelength. So the wavelength, the distance, a lot of time, this distance right here is in nanometer from crest to crest or from trough to trough. And for visible waves, with the waves that fall into the visible range that we can see with our eyes, it is the wavelength of the wave that determines the colors of the lights. For an example, here is a red light right here. And in this red light right here, the wavelength of it is equal to 750 nanometer. Versus here is a yellow light right here, and for a yellow light, its wavelength is actually shorter. In this case, 580 nanometer. And for a purple light, its wavelength is now 400 nanometer. So again, for visible waves that fall into the visible range that we can see with our eyes, it is the wavelength that determines its color. So please understand what the term wavelength means and how we can distinguish among waves of different wavelengths. And the next one that we also want to discuss will be the frequency of the wave. The frequency is basically the number of cycles that pass through a stationary point in 1 second. So let's say here is a stationary point right here. So in 1 second, how many cycles of a wave will pass through this stationary point? Then that is known as a frequency. So you can see, so this section right here is about the same at this section and about same at this section. And in this case right here, with this purple wave, we can see that there's more cycle that go through this same cross section right here compared to the other wave. So there's more cycle in here, and that kind of tells us that this purple wave right here have higher frequency compared to a red wave over here. So this is have lower frequency. And the relationship between wavelength and frequency is that they are inversely proportional. So this V right here, this is the symbol of the frequency. Frequency is then equal to C, which is the speed of light, divided by the wavelength. So they're inversely proportional. The higher the wavelength, then the smaller the smaller the frequency would be, and vice versa. So in this case, because this wavelength right here is 400 nanometer compared to 750 over here, so this one right here will then have higher frequency. So the term frequency, when it comes down to a wave, is often associated with energy of the wave. So the higher the frequency of the wave, then the higher in energy that wave would have. So the wave carries more energy within it. And overall, this is the electromagnetic spectrum right here. So we can see that the visible lights that we can detect with our eyes comprise only a small fractions of all of the wave in this electromagnetic spectrum. So here are basically example of all the wave with various in the wavelength. And so you can see wave on this right side right here, I'll have very small wavelength versus much larger wavelength over here. And the electromagnetic spectrum can be broken down as follows. First one, we have radio wave. Radio waves have very low energy in them, and their wavelength can vary anywhere between 10 to the 5th meter to about 10 to the -1 meter. So these are really big wave right here, with waves with very long wavelength. And after the radio wave, we will then have the microwave. And the microwave now have shorter wavelength compared to radio wave, so therefore have higher energy. So on this right side right here, the more on the right side it is, then the higher in energy it would be. And after the microwave, we will then have the infrared radiation. So infrared radiation are basically heat wave. That's another name for heat wave. And the wavelength of heat wave is anywhere between, again, about 10 to the -3rd to 10 to about -6 meter in here. And after that, we will have the visible light. So these are the light right here that we are capable of detecting using our eyes. And waves that fall into this region right here have certain color to it. And dependence on the wavelength, they have different color in them. And as we have seen already, red color or red wave have higher wavelength compared to the violet wave. And here in this case right here, we will then see that violet wave will have higher energy compared to red wave. So these have lower energy. And after the visible range, we will then have the ultraviolet radiation, and then after that the X-ray and the gamma ray. So these are some of the highest energy types of radiation that we have.